In this function, we have a number of things we need to figure out. The first two of them we can get using Descartes' rule of signs. We see that the powers of x in this function are already in descending order, so we can just look for sign changes. We have a positive to a negative term here, and a negative to a positive term here. Those are the only two sign changes in the function, and that tells us we could have two positive roots. Of course, if we don't have two, we have to have an even number less. So if we don't have two, that means we'd have to have 0 positive roots. As far as the number of negative roots, we need to first write the function for f of negative x. If I plug a negative x in for all these x's, my first term will come out negative because we're sending a negative to an odd power, which will switch its sign. The second term, we're sending a negative to an even power, so the sign will not change. Here we're sending a negative to an odd power, the sign will change. And at the end we have a constant. So we can see in f of negative x, there is only one sign change, which means f of x only has one negative root. To figure out how many imaginary roots there are, you need to think back to how many total roots there's supposed to be. The degree here is 3. The fundamental theorem of algebra says there must be 3 roots. So look at all your possibilities that you found so far. You might have 2 positive roots with that 1 negative. Well, that would be all 3 roots right there. That means there wouldn't be any imaginary roots. Another possibility is that you don't have any positive roots. You still got that 1 negative, but you're supposed to have 3 total. Well, 0 and 1 is only 1. We need to get to 3, which means there must be 2 imaginary roots if that were the case. Next, we're supposed to list all possible rational roots. Well, the rational roots theorem says if there are any rational roots, you can get them by generating a list of all the factors of the constant term at the end. So let's see, 1 goes into 4, 2 goes into 4, and 4 goes into 4. Over all the factors of the lead coefficient. So 1 goes into 3, and 3 goes into 3. Your possible rational roots then come from all the fractions that you can make out of these combinations of numbers. So these will be all the numerators in your fractions. These will be all the denominators in your fractions. So for instance, you could have 1 over 1 from this list, which is 1. You could have 1 over 3. You could have 2 over 1, which is 2. You could have 2 over 3. And you could have 4 over 1, which is 4. And you could have 4 over 3. Should have made my space bigger. The last part where it says to list the actual rational roots, well, to do that, you can start plugging the possible roots in to the function and seeing which one gives you a 0 remainder. So I'm going to set up a synthetic division or a synthetic substitution problem. And I'm going to start trying numbers in this list. Now, I could have two positive roots. I might not have any. I definitely got a negative root. I'm going to gamble on positive 1. I'm going to try positive 1. We'll see if we get a 0 at the end. So to do the synthetic process on this, we do. Yay. Not only that, but in the process, we've also got a new polynomial that'll have at least some of the same factors as the original problem. So our new polynomial is going to be 3x squared minus 11x minus 4. This might just factor, unfoil. So if it does, it'll have two easy to see roots, and those two roots will be roots of f of x as well. I'm going to clean up some space here. So 3x squared minus 11x minus 4. If I try to factor that, 3x squared comes from 3x times x. 4, I think if you try 1 and 4, we need different signs to make the negative. So if we do like plus and minus, and then if we check that guess, we get a minus 12x plus 1x. That would give you that negative 11x in the middle. So my actual roots, we already found out 1 works because we plugged that in the synthetic division problem. Then we got this reduced power polynomial, this depressed polynomial, that we factored. If we set this equal to 0, we'll get 2 roots for it. Those will also be the last 2 roots of the original function. So here, this factor, we'd have to have x be negative 1/3, which you'll see is in the list too. And this, we'd have to have x equals 4, which is also in the list. So these 3 are actual roots for the function.